Hello, in this lecture we shall talk about curves in polar coordinates. You can see this equation here, r equals r of theta. This is usually how curves in polar coordinates are given. However, if you have an equation like this, you can always use what you know about parametric equations, because from here we can write parametric equations for the curve. We know that x equals r cosine theta, so that we can write x equals r theta cosine theta. Same way, y is r sine theta, y is r theta sine theta. And you have two parametric equations where theta is the parameter. Usually theta goes between 0 and 2 pi if nothing else is given. This is interval, the default interval. So from polar curves we can go to parametric curves right away. Nevertheless, it's good to learn how to work with polar curves directly, and sometimes we also want to convert to Cartesian coordinates. Here are examples. We're given this polar curve, 4 times secant theta, just this. Find the Cartesian equation for this and identify the curve. So we have to eliminate r theta using the equations for x and y. Well, here we can write the secant in terms of cosine, because the relation between x and y, r and theta, is cosine and sine. It's good to use cosine here like that. And then we have this polar curve. If we multiply both sides by cosine theta, what we get is r cosine theta equals 4. But on the left side we have nothing else but Higgs. But x is 4. This is the simple Cartesian equation which corresponds to this polar curve. This is a vertical line where y is arbitrary and x is 4. It looks like that here on the coordinate system. Let's say number 4 is here, and you have vertical line, x equals 4. That's it. This simple line has a sort of complicated polar equation. Another example. Do the same for the polar equation r equals 2 times sine theta. Again, we had to eliminate theta and r, find Cartesian equation. So we can again use the basic equations. X is r cosine theta, y is r sine theta. If we replace here r by 2 times sine theta, we get x is 2 times sine theta cosine theta, y is 2 times sine squared theta. We can write x like sine 2 times theta, but it is not helpful because we just want to eliminate theta, not to write it differently. So how can we do this? I can use the equation that sine squared plus cosine squared is 1. let's take x squared. This will be 4 sine squared theta cosine squared theta. And we can actually find y participating here, because I can write this like 2 times 2 sine squared theta and then cosine squared theta, and we can find y as part of this expression. So x squared we can write 2 times y cosine squared theta. Cosine squared is 1 minus sine squared. Let's write it this way: 1 minus sine squared theta. So here at this point we have x squared equals 2y minus 2y sine squared theta. 2 times sine squared, look, this is y. So this is 2 times y minus y squared. And that's it. We eliminated theta and r. We have Cartesian equation. Let's write this again. We shall bring everything on one side. This is the equation: x squared plus y squared minus 2y equals 0. What equation is this? What is this geometric object? This is actually a circle, and to see this we have to complete the perfect square using these two terms. If you take y minus 1 squared, this will be y squared minus 2y plus 1. So we can add and subtract 1 here and write it x squared plus y squared minus 2y plus 1 minus 1 equals 0. This 1 we shall bring on the right side, and here we have x squared plus y minus 1 squared equals 1. We can recognize here a circle with center 0, 1 and radius 1. I want to remind you immediately that if you have equation x minus x0 squared plus y minus y0 squared equals r squared, this is a circle centered at x0, y0, and radius is r. So here x0 is 0, y0 is 1. This is how the circle looks like. This is the point 0, 1, and the radius is 1, so the circle has this center. It's like that. Pretty nice circle. Okay. Here is another example. Given is the polar equation r squared sine 2 theta equals 1. Eliminate r and theta, write Cartesian coordinates, and if possible identify this curve. So what to do? I can write this way. R squared will be 1 minus sine 2 theta. And r itself will be 1 over square root sine 2 theta. Using only positive r to make the computations easier here. And we have x equals r cosine theta, so cosine theta divided by this, and y will be sine theta divided by this. So what next? Take x squared and y squared. X squared will be cosine squared theta over sine 2 theta. Y squared will be sine squared theta over sine 2 theta. And here we can use this formula that sine 2 theta is 2 times sine theta cosine theta. So x squared will be cosine squared theta, 2 times sine theta cosine theta. Reducing by cosine, this is cosine theta over 2 times sine theta. So this is 1/2 cotangent theta. Y squared will be sine squared theta over 2 times sine theta cosine theta. This will be sine theta, again 1/2, and what is left is cosine theta. So this is 1/2 tangent theta. We all know that tangent theta is 1 over cotangent, so this is 1/2 1 over cotangent. Just a second. This is 1/2 1 over cotangent theta. Cotangent theta, 1 over cotangent theta, we can find from x squared. Cotangent theta, this is 2 times x squared. 1 over cotangent theta is 1 over 2x squared, which we can put right here. And we come to the equation y squared equals 1 over 4x squared. Okay. Here we can take squares of both sides and write y equals plus minus 1 over 2x. We have two hyperbolas coming from here. This solution looks complicated. If you think that this is complicated, you're right. I started this work just very formally using the basic equations without much consideration, and naturally it gave these equations. However, if we are more careful, we can reason this way. Again, from the same equation, r squared sine 2 theta equals 1. Remember, we use the formula for sine 2 theta. Why not we use it from the very beginning? This will give me r squared multiplied by 2 sine theta cosine theta. This equals 1. And then I can actually distribute r squared. R squared, I can write r times r and put r with sine, r with cosine, and then this will be 2 times r sine theta multiplied by r cosine theta, and this equals 1. Here obviously we can recognize y and x. So we have the equation actually 2xy equals 1. If you solve for y, you get 1 over 2x. So we're coming practically the same equation, and we don't have to wonder about plus minus. We see that we had to go with plus, because here we haven't taken any roots whatever, so they just this hyperbola. This solution is much better, but we have to figure out how to do it. Okay. Now, another type of problem. Given equation in Cartesian coordinates, write the polar equation corresponding to it. Find a polar equation. Polar equation means equation in polar coordinates. Let's start from something very simple. Let's take the line y equals x. That's a bisector of the first quadrant and the third quadrant, very simple line. What will be the polar equation for this? So we know the basic equations, we start from them. X equals r cosine theta, y equals r sine theta. So we write r sine theta equals r cosine theta. This is from the Cartesian equation. Reducing by r, we come to sine theta equals cosine theta. And this will give me, if you divide by cosine, this will give me tangent theta equals 1. We can solve here for theta. Tangent theta equals 1 when theta is pi over 4. And also theta is 3 pi over 4. Anyway, this is our polar equation. There is nothing said about the radius, so the radius is arbitrary. We can even take it negative. And if you draw our angle first, pi over 4 is this angle. You can move along this arm of the angle up and down, and allowing negative radius, or using also theta equals 5 pi over 4 in the third quadrant. So you have this entire line. That's our original line, y equals x. So this line has a simple equation that is pi over 4. It's not always like that. If you take another line, let's say simple line 3x minus 1, and let's see what is the polar equation. We replace x and y correspondingly by polar coordinates, so this will be r sine theta equals 3r cosine theta minus 1. We solve for r. We can write it this way: r sine theta minus 3r cosine theta equals negative 1. We can factor r, and this will be sine theta minus 3 cosine theta equals negative 1. And from here, r equals negative 1 sine theta minus 3 cosine theta. We can make it a little bit simpler if you multiply top and bottom by negative 1 and write r equals 1 over 3 times cosine theta minus sine theta. Look at this equation of a straight line. Impossible to recognize if you start from here. So polar coordinates are good when we describe objects like circles, and even sometimes parabolas look good in polar coordinates, ellipses, hyperbolas. Straight lines don't look very good in polar coordinates. Now, let's take one parabola. Let's work with the parabola x equals 4y squared. The axis is along the real line, horizontal axis, and the vertex is at the origin, 0, 0. What will be the polar equation for this? We're writing r cosine theta, so replacing xy by the polar equations. This will be 4 times r sine theta squared. So this will be 4 times r squared sine squared theta. Let's write this again. R cosine theta equals 4r squared sine squared theta. We can reduce by r, and this way we get cosine theta equals 4r sine squared theta. Solving for r will be cosine theta divided by 4 times sine squared theta. This is our parabola. Again, difficult to recognize. Difficult to recognize. Now let's look at one hyperbola. Very simple hyperbola. X squared minus y squared equals 4. Again, replacing xy by the polar coordinates, we have r cosine theta, all this squared, minus r sine theta, all this squared, equals 4. R squared cosine squared theta minus r squared sine squared theta equals 4. We can factor r squared, and here we get the cosine squared theta minus sine squared theta equals 4. Cosine squared minus sine squared, that's not the one, but there is another formula. Actually, you can write this 2 times cosine squared theta minus 1. If you think this is simpler, I can put it this way. Anyway, solving for r squared, we have r squared equals 4, and let's write it this way: 2 times cosine squared theta minus 1. This is our hyperbola. Again, difficult to recognize. So now we learned how to convert from Cartesian to polar coordinates, converting curves also, and to plot curves. We know how to do this very easily with Cartesian coordinates. With polar coordinates, we can use the graphing calculator. It should be in polar mode and always radians, of course. At the same time, it is good to plot by hand, polar curves plotting by hand. Graphs by hand. So I want to show you such examples. And we shall take the curve r equals 1 minus cosine theta and plot by hand, no calculator, without converting to Cartesian coordinates. So how do we work in such case? Well, I shall do a table where I shall assign values to theta and r. We're moving theta and constructing radius. Starting from 0, that's very natural. When theta is 0, cosine is 1 and the radius is 0. So we are at the origin. Then we increase theta counterclockwise, and look, I shall write one coordinate system, and talking, I shall also construct graph our curve. So we are now at the origin. Theta is 0. Then we move counterclockwise, increasing theta. We move to pi over 2. That's a very natural point. Here cosine becomes 0, r becomes 1. This will be the maximum value when cosine is, oh no, when cosine becomes negative 1, this will be the maximum value. So let's do this. Let's say 1 is here on the y-axis. Angle is starting from 0 and increasing. We're coming to this point when theta is pi over 2. Then we're moving to pi. Then cosine becomes negative 1, radius becomes 2. This will be the maximum value. So pi, this is straight angle, and the radius has to be 2. 1, 2. We're coming to this point. Angle is increasing counterclockwise. Radius is increasing from 1 to 2. Next interesting point is when we have 3 pi over 2. Then the cosine is 0, we have 1 again. 1 for the radius, and we, angle moves from pi to 3 pi over 2. We are following like that. Radius is decreasing from 2 to 1. This is the point 0, negative 1. Cartesian coordinates, but I'm writing 1 for the value of the radius. And then we're completing to the interval to 2 pi. Theta is 2 pi. Cosine is 1. Radius is 0. So we have to go moving counterclockwise from the point here with radius 1 to radius 0, like that. Oh, let me do this better. This part here. It has to be symmetrical. So we're getting something like this. By hand, this is the most I can do. This curve is called cardioid. It's an important curve in mathematics. It appears in various situations. And you see how we can do this by hand, by just following the angle and the radius. I'm choosing points like 0 pi over 2 pi, 3 pi over 2, 2 pi, because they are actually the most important for the cosine. Drawing by hand is important because you get more better acquainted with the curve. If you just use the calculator, sometimes you can get mistakes. Let me give you one example. Look at the circle that we did before. We had this equation, and let's put it by hand. R equals 2 times sine theta. 2 times sine theta. Remember, we converted to Cartesian coordinates. This was a circle with center at the point 0, 1. Now I want to graph it using my table. here 0. This was the center of the circle, but suppose I don't know anything, starting with my table. Again, theta r, and we're starting from 0. So we again at 0, 0. Theta is increasing from 0 to pi over 2, moving counterclockwise. Radius is increasing, sine becomes 1, radius becomes 2. So at beginning radius is 0, then radius becomes 2. So it's something like that, coming to radius 2. Then we're moving to pi. Sine goes from 1 to 0, and radius becomes 0. Here it is. When it becomes pi, radius is again at 0. We closed the circle. This is the entire circle. Then if we go to 3 pi over 2, sine will become negative. We have to use negative radius. And when we are moving through the third quadrant, we have to measure on the other side. So we are tracing actually the same circle again. When angle is 3 pi over 2, radius will be negative 2. And we have to measure on the other side. So we're repeating the same circle. So this circle is traced only once. For theta moving between 0 and pi. If you're doing this circle, this polar equation on the graphing calculator, you may not notice that if you're moving from 0 to 2 pi, you'll trace twice. And this will be a mistake. If you want to find area of this circle or similar curves, you need to know exactly the interval where theta moves. And you don't want to trace it twice. Okay, so graphing by hand, plotting polar equations by hand is very helpful, and such simple table helps. And I would advise you to do this by hand. Of course, you can use the graphing calculator to visualize the object, but understanding it better is when you're working with a table and drawing by hand. Okay, enough for this lecture. Next time we shall study tangent lines and areas. Goodbye.